Section 7.2. This talks about trigonometric integrals. One thing I always recall, we need to know some formulas from integral, like sine square x plus cosine square x is 1. And you know from this one you can always solve for sine square in terms of cosine, 1 minus cosine square, and cosine square in terms of sine square, 1 minus sine square. Also, we know we have the 1 plus tangent square x is secant square, and 1 plus cotangent, we need all these formulas, cosecant square x. Keep in mind, from here we can always solve for secant square x minus 1 to be tangent square. Same thing for the other one. We also need the double angle formula for sine 2x and cosine 2x. For the first one is 2 sine x cosine x. This one has 3 formulas. First formula is cosine square x minus sine square x, or has 2 cosine square x minus 1, or 1 minus 2 sine square x. From this cosine formula, double angle formula for cosine, say I want to take one of them. Say I want to take the cosine 2x, which is 2 cosine square x minus 1. I can solve for cosine square x. So 2 cosine square x, 1 plus cosine 2x. Divide everything by 2. Okay, we got a formula for cosine square x. Not only that, from here, this is good to know, important to know, you are allowed to multiply the highlighted angles by any number. Say by 2, for example. So that would make it 4x divided by 2. You can multiply any number. Or divide. Same thing, if I take that formula, double angle formula, that involving sine only, I can find formula for sine square, which is 1 minus cosine 2x divided by 2. So this will help a lot when working with trigonometric integrals. Also, when we are integrating sine x, you already know what that is. You know it's negative cosine, right? But so you know it's negative cosine x plus c. But how about if there's a number there, m, like a constant? You can do u sub mx is u, but it would be easier if we can go with straightforward 1 over m, cosine mx plus c. Same thing with cosine mx, the x, it's 1 over m sine mx plus c. As long as m is a constant. If we try the sine 4x, let's move on. So this would be 1 over 4 cosine 4x with a negative plus c. And to practice more on this, try cosine 1/3 x dx. Try this one. Same way. And the following one. Okay, we can move on. For this one, again, it's 1 over that number, sine 1/3 x plus c, which can be rewritten as 3 sine 1/3 x plus c. Next one, I see a 2 in the denominator. What can I do with that 2? You can pull it outside just for simplicity. You can pull it outside as 1/2. And now you're integrating 1 minus cosine 2x all dx. Keep the 1/2 out. The integral of 1 is x minus the integral of cosine 2x is 1 over 2 sine 2x plus c. So then you can multiply the 1/2 in to simplify this bracket part, and don't forget the plus c. Now we look at integrating sine square x dx. So here the sine square, what makes the sine square difficult is having the square on the top. So what we need to do here is to reduce the exponent from a second degree down to a first degree exponent. And that's why we came up with these formulas and boxed them, because we're going to go back and use them like this one. That's what sine square. It's 1 minus cosine 2x over 2. So it's the integral of 1 minus cosine 2x over 2 dx. And notice this is the same as the previous example, which give us 1/2 x minus 1/4 sine 2x plus c. Let's look at this one, cosine 4x. So again, the goal here is to bring the square down to a first degree trig function. We go back to the boxed formulas. We have one of them we proved. It says cosine squared 1 plus cosine 2x divided by 2. And what I'm gonna do here, I need cosine 4. I only have x. So I highlight all the angles that I have in the formula on the right side, and I need to multiply the x by 4. So that gives me 1 plus cosine 8x divided by 2. Now I can substitute that So we're gonna rewrite this as 1 plus cosine 8x divided by 2 dx. So here we pull the 1/2 out, 1 plus cosine 8x dx. Keep the 1/2 out. This 1, what is the 1? 1x. This is 1/8 sine 8x plus c. Multiply the 1/2 in. So this kind of problem is slightly different. It's not just sine or only cosine. We have sine and cosine involved. So the way these things work is we look at the one with odd exponent. This is the odd exponent. If one of the function has odd exponent, we save a copy of that sign, one of it, next to dx, and that will make it sine square x, and the cosine to the fourth x stays the same. So we save a copy of sine, and we'll see why we're doing this, and then convert. So save a copy of sine, convert the remaining, which is this, into cosine, 1 minus cosine square x. Keep this the same, keep this the same. Then, now we take our u to be cosine x with u substitution. So du is negative sine x dx. So we put a minus there, a minus outside. So we need the minus, 1 minus, cosine is u, so u square, u to the fourth, and all of this is du. Multiplied by negative, so negative u to the fourth plus u to the sixth du. Now it becomes negative u to the fifth over 5 plus u to the 7 over 7 plus c. Then we replace the u back with cosine. So cosine to the fifth of x over 5, cosine 7th x over 7 plus c. So again, the steps were save a copy of sine x, convert remaining to cosine, then let u equal cosine x. So every time you have sine cosine within one integral with different exponents, take one, the odd one, save a copy of it next to dx, convert the remaining to the other one, and then use the u sub. We can write another problem, cosine to the fifth x over the square root of sine x dx. Good to try this one. So here I see the cosine has an odd power. Maybe I want to save a copy of cosine, and I'll leave cosine to the fourth x and keep the sine as is. So now what we need to do is, remember how we need to convert the remaining into sine. So I know that cosine square x is 1 minus sine square. So if I square both sides, that will give me 1 minus sine square x square. So that would give me 1 minus sine square x square. Cosine x stays the same, and the denominator stays the same. So u here is sine x. Du is cosine x dx. So this is our du. So it's gonna look like 1 minus u square square du over the square root of u. So you got 1 minus 2u squared plus u to the fourth, and the bottom can be u to the 1/2 du. Then then there's many ways to proceed from here. One way is to rewrite that u to the 1/2 by bringing it up and then multiply. So, or you can split, keep this the same, bring it up, becomes u to the negative 1/2. We multiply, we get negative 1/2. 2 minus 1/2 is 3/2. U, 4 minus that, 7/2. So then u to the 1/2 and over 2, which becomes that. U to the 5/2, 2/5. U to the 9/2, 2/9. U is the sine x to the 1/2 minus 4/5. U is sine x to the 5/2 plus 2/9 sine x 9/2 plus c. So most of these examples we dealt with either was only sine or only cosine or both sine and cosine involved. How about other trigonometric functions like secant and tangent? Good to recall from before that secant tan as a formula, the integral of that is simply secant x. And good to recall that the integral of secant square x is simply tan x. So by knowing these two formulas, we're going to build on them and try to integrate more difficult trigonometric integrals, such as this one. So the way this works, in order for the integral to work out, this is the guideline. If tangent tan has positive odd exponent, we save a copy of secant tan and convert remaining into secant x using the formula tangent square x equals secant square x minus 1. So for example, secant cube 3x, I'm gonna I save a copy of secant 3x tan 3x dx, and the tan square 3x. So I saved a copy of secant tan, and that will give me 2 copies of tangent and 3 copies of secant. Then it says convert the remaining into secant. So convert means the tangent, convert them into secant square 3x minus 1 and bring all that down. Why did we save the copies? Because now we can say take u to be secant 3x. du is 3 secant 10. So I need a 3, there's a 3 missing, and 1/3 out. Then I keep the 1/3 out. Secant is u, so you get u cubed times u squared minus 1 times du. And then it's not difficult to integrate something like this by multiplying the u cubed first to u to the 5th minus u to the 3rd du. Then this will give me 1/3 u to the 6 over 6 u to the 4th over 4 plus c. U is secant, so secant to the 6 of x over 18 minus secant to the 4th of 3x over 12 plus c. Another common example that we do in tangent and secant is something like this: tangent square, integrate tangent square. To me, when I do this, I always go back to the form. It's like, okay, what's the derivative of secant? It's secant tan. That helps me. And what's the derivative of tangent? It's secant square. So I'm thinking backwards, like how can I go backwards from here to there or from here to here? Well, I don't know if I can get secant tan, but I know a relation between tangent square and secant square that we introduced at the beginning of this section that says I can replace tangent square with secant square minus 1. Why did I do that? Because if I know the secant square, I can find its antiderivative. So the antiderivative of secant square is tangent, and the antiderivative of 1 is x, and don't forget the plus c. How about to the 4th power? Tangents to the 4th, to me, I was like, again, there's no formula for that, but I can rewrite this as tangent square x times tangent square x. And remember how I switch or change tangent square? I convert it into secant square minus 1. So then you multiply this out minus tangent square x dx. Now we can split this into two integrals, keep this the same, minus this one here, like that. Now we did integrate this earlier, but for this one, can we do u sub? If I do u equals tangent, u prime is secant square. Oh yeah, u works here, u sub. U equals tangent, du is secant square x dx. So that would be u du basically. U means u square over 2. So that's tangent square x over 2 minus we found the integral of that one, tangent x minus x, when we integrated tangent squared plus c. So then all we have to do is, wait, u squared, that should be u cubed over 3. So that would be 1/3 tangent cube x minus tangent x plus c. Another common one that people ask and you come across the whole time, how about just tangent x? People say, hey, can I do, which you've seen that before in Calc 1, but good to recall it. The way to do tangent is just rewrite it as sine over cosine, and then we do the u sub. U equals cosine x, du is negative sine x dx, like that. So you need the negative with negative, so that would give me negative du over u. So this gives me negative natural log of u plus c, negative natural log of cosine x plus c. Another thing we do in integrating or working with trig integrals is sometimes you need to know formulas from pre-calc, like trig formulas, to actually be able to integrate stuff. It's not about, oh, I can't integrate it, but you can integrate it not because you don't know the integral part, but you don't know the trigonometric formula behind it. So for example, in pre-calc we introduce what we call product to sum formulas. If you have a product of two trig formulas, like let's say sine alpha, cosine beta, and there's 3 more of these, it's 1/2 sine alpha plus beta plus sine alpha minus beta. So for the homework, you can always refer back to the formula sheet. And on the test, it depends. Sometimes some teachers, they give you the formula and say apply it. Sometimes you have to memorize it. But how do we apply this in integrals? Well, let's say we're integrating sine 5x times cosine 3x dx. So here, the way this works is the integral. The formula said 1/2, and let's do this dx, sine the sum, right, sine the 5x plus 3x, plus sine the difference, 5x minus 3x. And that would give, pull the 1/2 out, that would give me sine 8x plus sine 2x. By converting or using a product to sum formula, it turns the integral into a simpler version of it, where I can integrate the first one as 1/8 with the minus cosine 8x, 1/2 cosine 2x with the minus, and don't forget the plus c. So this looks like sine mx, sine mx. So it's 1/m. Now we multiply the 1/2 in, negative 1/16, cosine 8x, 1/4 cosine 2x, plus c.